Okay, let's continue with our discussion of Zener diodes. So any questions before we begin? Okay. All right. Let's see. Class notebook. All right. So I believe we stopped here where we are looking at a single Zener diode connected in reverse bias to a voltage source, VSS. Okay. Brief recap. If VSS, the supply voltage, is less than the Zener diode voltage, it's not going to turn on. Okay. If it's higher than VZ, then it'll turn off. Turn on. So let's perform an analysis of this Zener diode, a load line analysis. So we are familiar with the load line analysis from the silicon diodes or just any kind of diode. The approach for Zener diode will remain the same. So the given values are that the supply voltage VSS is 15 volts. We are not given the Zener diode voltage. We are given the value of the resistor R, which is 1 kilo ohm. So again, R is right here, and this is the Zener diode, okay, and VSS. So R is 1 kilo ohm. Zener diode voltage VZ is not given to us, okay. What is the output voltage V out? So V out is the question. VZ is unknown. And that is actually what we need to find, right? This is what we're trying to determine. VZ is unknown. So let's apply KVL or KCL. In this case, since I want to find the voltage, KVL makes the most sense. So if I apply KVL this direction, I get the supply voltage VSS, voltage across the resistor, and the voltage across the Zener diode, right? Only two. And for reference purposes, I will stick, just for this example, I'm going to stick with the minus and plus sign as shown in the diagram, which means minus is at the cathode and positive is at the anode. So if I sum up the voltages, this is what I would get. VSS, or actually minus VSS, plus VR, voltage across the resistor R, and minus VZ or VD. In this case, VZ is equal to minus VD. So let me just write VD is equal to 0. Now, I always make it a point to state, if you have a preferred method of applying KVL, do not be forced to do what I am doing. Okay, I don't force students to do the exact same method that I do. Everybody has their own preferred way of applying KVL. So if you know something that works for you, just stick with it. So I would get VSS is equal to VR minus VD. VR, of course, is the current, and the current is, well, it should be, if I stick with the convention again, I would get minus ID. So I would get minus ID times R minus VD. Okay. That's my KVL expression. VSS, the supply voltage, is equal to the diode voltage plus the resistor voltage. Two unknowns in the circuit, VD and ID. Load line analysis means we are plotting a linear line that intersects the diode characteristic. So we want to find the values of those two voltages and currents. we plug in both quantities as 0. So VD is 0, and we find ID. And we find ID, and then we plug in ID as 0, and we find VD. So in this case, if I plug in VD is equal to 0, ID turns out to be minus VSS over R, which comes out to be 15 divided by 1000, and then actually minus, so minus 15 milliamps. Right? Makes sense? Same thing for ID is equal to 0. VD turns out to be minus VSS, so minus 15 volts. Same analysis as the one for the diodes. Yes. Where here in the graph? No, ID, yeah, if you plug in ID as 0 volts, you get VD as minus 15. Oh, right here. Thank you. 0 amps. Yes. So ID, because the reference for a diode, it always goes from anode to cathode, and we are working in reverse bias. So the negative sign indicates we are working in reverse bias. But again, key thing that I pointed out last class was even if we take the diode voltage and diode current as positive from anode to cathode, Zener diodes are used in reverse bias. So if we say diode voltage and diode current for a Zener diode is negative, but we refer to Zener voltage and Zener current simply as positive. And so that sometimes gets confusing. Okay, and again, just for this example, particularly, I will stick with a negative. But when we do the regulator, the next example, we'll just stick with a positive convention. Yes. It's the same. Right now, the circuit is simply VSS, R, and diode D. That's it. So we are not looking at a regulator circuit just yet. Just simple Zener circuit connected to a power supply. So we have two ends of the line. We plot it. We get minus 15 milliamps here and minus 15 volts here. This slope is exaggerated. It says accentuated slope, but I would say exaggerated slope. It should be a near flat vertical line. But again, this is a example problem. So for explanation purposes, the slope is exaggerated. Okay. All right. So once we have that, the intersection point, the coordinates of the intersection point gives us the diode voltage and the diode current. Load line analysis. So the coordinates here turn out to be minus 10 and minus 5. And so diode voltage VD is minus 10 volts. And then ID is minus 15, oh, minus 5 milliamps. Okay. At the same time, I could say VZ, Zener voltage is simply 10 volts. Again, plus and minus signs are for us humans. Electrical signals don't know whether they're positive or negative. If our supplied voltage is 20 volts, then the line shifts, and that is indicated by right here. So if VSS, or supply voltage, is equal to 20 volts, the linear line remains the same, but it shifts. And now my intersection point is right here. This is VSS is 20 volts. This is VSS is 15 volts. And my diode voltage and current is now shifted just a tad, minus 10.5 volts. And let's say minus 10 milliamps. Minus 10 milliamps. All right, let's take a pause. Let me know if you have any questions. Do the steps make sense? Right. And again, load line analysis is something we'll see again for transistors. It's an excellent way to analyze a nonlinear device by isolating the linear circuit and then applying a load line, creating a load line for that circuit. Okay, let's move on to the primary application of a Zener diode, Zener regulator. So we'll do both. We'll do a load line analysis of the Zener regulator. Now we are introducing a load RL into our circuit. The circuit remains the same, but now we have an actual load at the output. So we'll do a load line analysis, graphical analysis, and we'll also do a analytical analysis. And there are multiple possibilities within a Zener regulator. So let's look at that first. So here is our circuit. This is what is given to us: VSS supply voltage, series resistor R, Zener diode, VZ. Let's see. And then load RL. So given values, load RL. And that is given to us as 6 kilo ohms. R is series resistor. And that is given as 1.2 kilo ohms. VSS, the supply voltage, is something, let's see, is something that can be given, or if it's a design problem, then we need to find the range for VSS. In this case, it's given to us as 24 volts. But it can be an unknown. Pointing this out because, again, there are multiple possibilities when it comes to a Zener regulator problem. Okay, so the question being asked is determine the output voltage VL and the supply current or the series current IS. Okay, VL and IS. All right, let's begin. So what we're going to do is, because the Zener diode is a nonlinear device, we need to first find the voltage that is being applied to the Zener diode. The supply voltage is not connected directly to the Zener diode. So what do we have to do? First week, Messrs. Thevenin and Norton. I told you, you can't escape them. So we isolate the Zener diode, and you would find the Thevenin equivalent circuit as seen by the Zener diode. That means we redraw the circuit, isolate the Zener diode on the right side. And when I say isolate, I do not mean we are actually changing the circuit. I'm simply drawing it on the right side. Electrically speaking, there is no right or left. They are both in parallel. So VSS, series resistor R, and my load resistor RL. And my Zener diode is broken away, leaving behind two terminals of analysis, A and B. So I need to analyze the rest of the linear circuit. And remember, diode is nonlinear, resistors would be linear. So I need to analyze the rest of the linear circuit to determine the Thevenin voltage and the equivalent Thevenin resistance. So let's take a look at Thevenin resistance first. RT for this portion we have RL here, R here, and RT. Again, terminals of analysis are A and B. So RT is measured between A and B. And what do we do with the voltage source to find Req? We reduce it to 0, so we replace it with the short circuit. So what is RT? Absolutely, both are in parallel, and it becomes product of the two divided by the sum of the two, R times RL, R plus RL. So it's 1200 times 6000 divided by 7200. Comes out to be a nice even number, 1000 ohms. All right, let's take a pause, write it down. Let me know if you have any questions. Yes. So we can apply KVL, but that doesn't take into account RL. We need to find the actual voltage that is coming between the junction of R and RL. So if RL is in parallel with, so the question being asked is, can we simply apply KVL and solve it? Yes, but that would not give us the complete solution. We need to take into account the values of RL. And this is skipping over to the end of the problem. RL values right now is given to us. A different kind of design problem would ask, what is the range of RL that can be applied to this circuit? Because as you can see here, RT would change depending on the value of the series resistor R as well as RL. So in a design problem, you could change the values of R, you could change the values of RL. Let's say RL is given, and the question being asked might be, what is the minimum and maximum value of R that can be used in that circuit? Or value of R could be given, and we would be asked to determine the maximum range of values, minimum and maximum values for RL that can be placed in the circuit. The solution that we are doing in class right now, we are given R, we are given RL, we're asked to find what is the output voltage and the current IS. And at the end, I will do an example where we can determine the maximum range of the supply voltage. Okay. All right, so that was Thevenin resistance. Thevenin voltage, VT. How are we doing on time? 30. Go back to the original circuit. VSS, series resistor R, my terminals A and B, and I need to find the open circuit voltage between A and B. So what do you think? I mean, as far as circuits go, this is straightforward. What equation comes to mind? Voltage division, absolutely. There's only three equations, right? And I keep repeating the same thing again. Ohm's law, KVL, KCL. Everything else is a derivation from these three equations. Entire 201 that you did, it's these three equations. So voltage division is nothing but a shortcut. And voltage division gives us VT as a fraction of VSS. The fraction is given by RL or REQ. Now this REQ is different because it's series, R and RL. So therefore, Thevenin voltage simply 24 times 6,000 divided by 1200 plus 6,000. And this turns out to be 20 volts. Let's take a pause, then I'll make a statement or an observation. Any questions about how we found VT? Okay, so going back to that earlier question, right, about directly finding the answers. VT, the equation for VT, the Thevenin voltage that is being applied to that Zener diode, contains both R and RL. If either one of them changes, then VT changes. And if that VT is less than the Zener diode voltage, it's not going to turn on. And that's why in design problems, the values of R and RL are critical. So there is a range of values for both RL and R, minimum and maximum values. If RL is small enough, I mean, if RL is small below a certain level and R is larger than RL, then the supply voltage to the Zener diode, meaning VT, the Thevenin voltage, would be far smaller, and the diode won't turn on. Does that make sense to everyone? Okay. All right. So now we have our Thevenin circuit. And because we have our Thevenin circuit, I can write VT is 20 volts here. RT is 1 kilo ohm. The ID current, they still reference in the negative direction. Yes. In the forward bias, it functions as a regular diode. So back to our model here. Forward bias, regular normal diode, standard diode characteristic. In the reverse bias, it will be off until the reverse bias voltage crosses over its Zener voltage. Okay. All right. So where were we? Oh, so now we have a linear circuit. Same circuit that we analyzed on the previous page. Now we can apply KVL. So if you apply KVL for load line analysis, we generate a load line for VT and RT. And I can write on a straight way, right, VT plus ID RT plus VD is equal to 0. And this time I'm simply ignoring the polarity in the direction shown in there. Just keep things simple. But when we go to the graph, which is on the next slide, the graph is plotted in reverse bias, so I know the values are negative. And then to find the 2 points for the equation, if VD is equal to 0, then ID is equal to VT over RT. That gives me minus, well, actually, just 20 milliamps. And if ID is equal to 0, then VD is simply equal to VSS, which is 20 volts. All right, let's take a pause. Let me know if you have questions. At this point, let's say we don't know what VZ is, right? Again, it's load line. Characteristic is given to us, and it's right here on the next slide. So this is given to us, graphical analysis. And this is what we calculated and plotted. So minus 20 milliamps here for current, minus 20 volts for the voltage. The intersection point is the solution for the equation. So we get diode voltage as minus 10 volts, and diode current is minus 10 milliamps. Again, remember, 2 unknowns, right, for every problem. Voltage and current. We need 2 equations for graphical analysis, 2 plots. So we get 10 minus 10. Make sense? All right, questions? Yes. It actually doesn't matter. So you can go clockwise, you can go counterclockwise. Answers would always be same. Typically, so most students from their physics classes or from prior classes, they are used to taking like a voltage and then dividing up the voltage across all the components. So they get like supply voltage is equal to something. And I'm always used to like just writing all of the voltages out, equating it to 0. And then I put a plus sign, minus sign, plus sign, minus sign, however I go. That's what I always state. If you have a preferred method, stick with it. Okay, so let's go back to our circuit here. Now we solved this, we found the diode voltage, the diode current, right? If I wanted to find, let's say, the range, the maximum and the minimum range of the supply voltage, right? Extending this problem, extending the design problem, what would we do? So look at the circuit. What do we have in the circuit? How does this circuit actually work as a regulator? Let's say VSS is at a certain level. Let's say 15 volts, right? If it's 15 volts, the two resistors are going to split the voltage, and let's assume the diode turns on. So the supply voltage is going to supply some current IS. Let's just say it's 1 milliamp, random number. So 1 milliamp is coming from the supply voltage. Some of it splits. If you apply KCL at the top, it goes through the Zener diode and it goes through the load resistor. Now, the function of the Zener diode is to act as a regulator, or the application is to function as a regulator. If the supply voltage increases, the Zener diode must regulate the supply voltage so that the output voltage of the load resistor remains constant. If the output voltage remains constant on RL, that means the output current through RL must also remain constant, or at least within some small variation. So if Vs increases, the Is current coming from there increases. If Is increases, so let's say Vs increases, then Is also increases. But this shouldn't increase. IL shouldn't increase. So where is that extra current going? Through the Zener diode. So IZ must increase. And if current through a device increases, what happens to the power? Power also goes up. The power goes up. What happens to all that extra energy? Dissipated as heat, thermal energy, right? Device gets hot, hence power rating. So every Zener diode is spec'd with a power rating, which is what we pointed out here. When we buy a Zener diode, there is a power rating on the Zener diode. All right. And that is given as PZ. So let's say, for example, in this regulator, we have a Zener diode with a power rating of 1 watt. Okay. Let's say VL needs to be maintained at 10 volts. Hence, VZ, the spec for VZ that you would choose will also be 10 volts. And let's say we choose a power rating of 1 watt, but just quite large, just in general terms. Okay, for small electronic circuits, you will not go that high. So let's say that is 1 watt. And let's redraw the circuit down here. So then we have VR, we have the Zener diode, and we have RL. Plus minus VR, and I'm going to simply state VL. VL is equal to VZ. Those both are in parallel, right? And then this would be VSS. So if we want 10 volts to be supplied to our load resistor, we can calculate the minimum voltage that is required to turn it on, and that would be equal to VSS is equal to VR plus VL, right? The supply voltage is split across the series resistor and the parallel combination of the Zener diode and the load resistor. So far, so good. Supply voltage, VR, VL. Now, from here, we can write an equation for VSS min, the minimum voltage that is required to turn it on. And because it is breaking across both VR and VL, I can find VL as, oh, let's go down. RL or R plus RL. Again, voltage division. So you plug that into that equation and we can find a value for VSS min. So rearrange the terms. You get VL times R plus RL divided by RL. Still the same voltage division. Right? If we ignore the Zener diode, VSS is dropping across the series resistor R and across the load resistor RL. So we can find the voltage VL in the equation of voltage division. So VSS min can be determined as, now we want 10 volts for VL, and then R plus RL is 7200 divided by 6000. And so minimum voltage comes out to be 12 volts. And 2 volts will drop across the series resistor R. So let's take a pause, write it down, think over it. Let me know if you have any questions. All right, let's see. Sign convention around KVL. Does that make sense? If you want to find, so in this case, the design problem is what is the range of the supply voltage? Because that's a primary function of a Zener regulator. Supply a constant voltage to the output, no matter what is your input. So the question would be, how much can your supply voltage fluctuate and still maintain the output voltage constant, right? So we'll have a maximum range, right? That cannot be exceeded by the supply voltage, but there's also a minimum value that cannot be, the voltage supply cannot be lower than that minimum value. Otherwise, your Zener diode would not turn on. If you supply 11 volts or 10 volts, for instance, that 10 volts is now going to drop across RL and R, divided across both of them. And so if your Zener diode is 10 volts and your supply voltage is 10 volts, it's not going to turn on. If you supply, excuse me, sorry. If you supply 11 volts, some of it is still consumed by the resistor R, some of it goes to the Zener diode and RL, it still wouldn't turn on. According to these specifications, your supply voltage must be a minimum of 12 volts. If it's 12 volts, 2 volts drops across R, the rest of it goes to Zener and load resistor 10 volts. Okay. So that's the minimum value of the supply voltage coming from the input. If maximum voltage, sorry, not if, maximum voltage cannot be exceeded, that's where the Zener power, PZ max, comes into the picture. Because any extra current or extra voltage that's coming from the power supply, the Zener acts as a current sink. It has to sink the extra current. And so if PZ max, in our example, is 1 watt, we can calculate the maximum current that can be handled by the Zener diode. So VZ is 10 volts, and therefore IZ max is equal to 0.1 amp or 100 milliamps, which, as I said, is a large number. Okay, 100 milliamps of current is a large number. So if that's the case, now we can apply KCL at the top and find IS as IZ plus IL. IZ plus IL. But what is IL? Ohm's law, right? So we had KVL, we had KCL, now we have Ohm's law. VL is the same as VZ, so it's 10 volts divided by 6,000 ohms, and we get 1.667 milliamps. This is the current that must be kept constant for RL. So if the supply current increases, the Zener diode must provide a pathway for the extra current to go through. If the extra current goes through Zener, IL remains constant. Does the concept make sense? Right. All right, let's take a pause. Let me know if you have any questions. And we have about 8 minutes left. Sufficient time to get through everything. All good? Okay. So then IS total cannot exceed IZ max plus IL. And IZ max in our case is 100 milliamps. IL is 1.667. And so the total current IS cannot exceed 101.667 milliamps. You don't want a trapezoid. Right. And thus, if maximum current is that is coming from the power supply is 101 milliamps, then the voltage drop across R cannot exceed is 1200. And so VR max cannot be more than 122 volts. Supply current is going directly into the series resistor. So supply current is 101. Voltage drop across the series resistor is 122 volts. And because our Zener diode or load resistor is 10 volts, that means our VSS max can only be 122 plus 10, which is 132 volts. So our final range is 12 volts and 132 volts. All right. Pause and then statements and then questions. Make sense? I hear I can see some nods. You're ready for a pop quiz. But Friday quiz coming up, so fair game. And mostly be based on Zener diodes, not mostly, almost entirely on Zener diodes. So it'd be Zener regulator or just load line analysis of Zener. Friday, Wednesday, and Monday. Sorry, Wednesday, Monday, and Friday. All right. Questions? Did the approach make sense? Possible questions, possible problem questions. So in this case, we were given the Zener voltage values, right? Zener voltage value is given, series resistor value is given, RL is given. And so we are asked to find what is the output voltage across the load resistor, and we are asked to find the series current IS. We can extend that from all the given information. Question can be asked, what is the maximum range of the input that is going into our circuit, into the Zener diode circuit? So that is one possible question, which we just did. Another possible question is, what is the minimum and maximum value? And I'm going to write this out on the side. Let's go back up here. So possible questions in this design problem. What is the minimum and maximum value of the series resistor? So R min and R max. Remember, we just saw the expression for the Thevenin voltage as well as the load voltage, right? So if R value is high, if it exceeds a certain limit, then not enough sufficient voltage will be applied to the Zener diode for it to turn on. And so there's a maximum limit for that R value. Approach would be the exact same. And then also there would be a minimum because we do not want that current to exceed. So if R series resistor is low in value, the current that is going into the Zener diode will be high. So if it's far higher, if the value for resistor R is lower than R min, then the total current coming from the supply and going into our circuit would be high. And then that would exceed the power rating for the Zener diode. So we call the KCL expression we applied. We would use that and do a back calculation. So we could find R min and R max from those steps. We could also find a range of values for RL using those same equations. RL min and RL max. Okay, so there will be a load, there'll be a range of the load values. Because again, if RL is smaller compared to R, again, we saw the expression in the equation, right? Not enough voltage would drop across that Zener diode. If RL is smaller than R, voltage division would imply Zener diode voltage is not going to be higher than 10. And so there's a lower range, and then there's also a maximum range of RL. So in terms of regulation, there are two terms. We can say line regulation and load regulation. Load regulation means our regulator, in this case Zener diode, will keep the output voltage constant irrespective of the value of the load. And that is load regulation. How well can the Zener diode maintain a regulated output voltage irrespective of the load? And obviously, this is not ideal conditions. So we have a minimum and maximum value. And then there is line regulation, meaning the line voltage that is coming from our input. How well can the Zener diode regulate the voltage irrespective of the input voltage coming from our supply? So again, supply voltage regulation would be line regulation. So supply voltage variations. And load regulation is load resistor variations. Oh, we're out of time. Okay, so Friday quiz and Monday quiz. Friday quiz based on, I would say 90% on Zener diodes and Zener diode regulators. And Monday quiz will be Monday, Wednesday, Friday of this week. Okay. So we'll end class here today, and I will see you all on Friday. If you have questions, I have another 6-7 minutes before next class. And again, homework is already assigned. It's already on there. I have to check the due dates. There's a Zener diode homework. The day due in a day or two. Okay. Who has any of you have finished the Zener lab? Okay. It's always because so it's like if it's earlier in the week, it's like Monday and Tuesday labs. It's hard to keep everything in track. Uh-huh.